Welcome to this introduction to exercise 18, measuring the diameters of Pluto and Charon from Astronomers as Observers and Experimenters, published by Kendall Hunt. I'm Jeff Wilkerson, professor of physics at Luther College. So we're going to provide a little bit of introduction to this exercise. It's interesting in a number of ways. It's one that I like to do with my students quite a bit. We don't necessarily do it every time we work through the course, but we do it more times than not. And this is, there are a few things that, as we've talked about many times with these introductions, there are a lot of different learning goals, and we're building these exercises around learning goals and thinking about how we grow in understanding how we develop knowledge of the universe. We have different goals related to that development here. Certainly, one of the learning goals for this exercise could be to measure the diameters of Pluto and Charon, so we get information about these two objects, this binary Kuiper belt object in the solar system. And it could also be to understand a technique that we use quite frequently, which is this occultation technique. You see two objects, and then suddenly one passes from your point of view in front of the other one, and it blocks, and you see one object or parts of two objects, and then they pass back out. Brighter when you see them both, dimmer when part of one of them is covered. And this is a technique that much more commonly is used for eclipsing binary stars than it is for planets like this, or Kuiper belt objects, or asteroids, or something in the solar system. But this is this is an example of this technique in the solar system. So learning something about this technique is also a very important learning goal in this exercise, I think. But in addition to that, how to process data, thinking about making linear fits to data, when linear fits are appropriate, when linear fits are not appropriate, and scatter in data. So sort of data analysis learning outcomes are interesting outcomes for this exercise as well. So let's backtrack to this idea. Let me draw a little bit on the board to talk about this idea of two objects, one object passing in front of your point of view. Again, we're talking about Pluto and Charon here, but we're going to talk about this broadly. This could be two stars in a binary system where one from your vantage point passes in front of the other. So this is you as the observer out here, and that's your line of sight along this direction. If you have two objects out here that are orbiting such that that orbital plane is aligned sufficiently with your line of sight, you will see this eclipse occur. For the Pluto-Charon system, this does not happen because things wobble around, because the orbits of things in the solar system aren't a perfect plane. Things are tilted a little bit relative to one another. We don't see this alignment occur very often. The data in this exercise came from 1987. And so only there's a great deal of time between eclipses of the Pluto-Charon system. For eclipsing binary stars, often you either see them or you don't see them, and they're very short periods. Often you can see there's one of these exercises in the lab book looks at data from an eclipsing binary system, and you can look at that now. And you see that you'll see these things often have very short periods, and you can check the geometry of that. If this is tilted up just a little bit, this orbital system, you're not going to see the eclipse. And so just to do the statistics, just to say there's a lot of geometry where these things are tilted such that you don't see an eclipse, very little geometry such that they're tilted where you do see an eclipse, whether you're talking about planet, moon, binary Kuiper belt object, or a binary star system. That geometry is going to hold true. So what we see and what's drawn for you in the exercise that you have pictured for you right there is to say, from your point of view, when you see one object start to pass across in front of the other object, you will start to see the amount of light from the system disappear. It doesn't matter whether this object is in front or this object is behind. Okay? And we call that the point of first contact. If this object is in front, then you're losing light from this object. If this object is behind, then you're losing light from that object. But all that matters is from your vantage point where you're looking right now, you're seeing this thing cross the line of sight. So up until that point, when it was out here moving in, we had relatively constant signal. You know, one of these things could be a variable. If you're talking about stars, it could be a variable star. So it might not be a perfectly constant signal, and there will be noise in your observations. There will be scattering from the atmosphere. There will be Poisson counting statistics in your CCD camera. There are all kinds of things that cause noise in the system, scattering in the signal that you measure. So the signal is not going to be perfectly flat. It's probably going to be jumping up and down like this. And we're going to work with this in this exercise. So you're going to take that into account a little bit. When we hit that point, the light starts to go away. And the light will go away steadily until we reach this point, where if this object is behind, it's completely covered, or if it's in front, it's got the maximum amount of surface area of the larger object covered. And at that point, so that's first contact right there. We call that second contact. And that's right there. And now it's steady light again as it moves across, right? So you've got a steady light in the system, no light leaving, no light entering the system until you hit that point right there, at which point we call that third contact. And you start to gain light again. So at third contact, the system starts to get brighter as you start to have both of these objects exposed again. And then we get out here, this is going to be fourth contact. And fourth contact is when the two objects have become completely free of one another again. And you see all of both objects. So that's what we got going on. That's what we're going to work with here. And if we know the velocities of these objects, in a binary star system, in an eclipsing binary star system, the standard way to do this would be to measure Doppler shift. You could certainly do this with planet, moon, or binary Kuiper belt object as well. And so, but to measure the velocity in orbit, you measure the Doppler shift as the stars. One star is moving towards you, it's blue shifted. One star is moving away from you, it's red shifted. You get the speed from Doppler shifts that way. If it's a circular orbit, not an elliptical orbit, then that speed is constant. And if that speed is constant, you just have to measure it once and you know what it is. So if you know the speed with which this thing has moved across here, what you see is going from first contact to second contact, the amount of time that, the amount of distance that was covered, you're going from the right edge of the smaller object in contact with the left edge of the larger object, to the left edge of the smaller object in contact with the left edge of the larger object. So you moved one diameter of the smaller object, okay? And so if you know this idea that distance traveled is equal to the speed times the time, if you can measure the time from first contact to second contact, and you know the speed from a Doppler shift measurement, or from just, if you assume it's a circular orbit and constant speed, you know the period of orbit and the circumference of orbit. If you know those things, something along that line to get you the speed, then you can determine the distance you traveled. And that distance, going from 1 to 2, is going to be the diameter of the smaller object. Going from 2 to 3 is going to be the diameter of the large object, right? No. Going from 2 to 4 is going to be the diameter of the large object. Left edge, left edge, left edge, right edge. So 2 to 4 is going to give you the diameter, the distance traveled from contact 2 to contact 4. You measure the time that way. You're going to have the diameter of larger object. 1 to 3 is also going to be the diameter of the larger object, and 3 to 4 is going to be the diameter of the smaller object. I hope you can look at the geometry there and convince yourself that that's the case. So we have 2 opportunities to measure the diameter of the larger object and 2 opportunities to measure the diameter of the smaller object. And you'll do both of those in this exercise. So what you want to do in this exercise, this is a light curve. So you make a graph of signal as a function of time. And signal as a function of time, it's going to be messy, as we talked about a moment ago. You're going to have Poisson counting statistics in your CCD camera or in your photometer in the case of the data that was taken here. And you're going to have Light is scattered. Scintillation in the atmosphere scatters out photons on the way. As the light comes through the atmosphere, photons get scattered out. Different amounts of photons get scattered out as a function of time. It's a statistical process. And so that's going to cause the signal to jump up and down. So there are all kinds of things that can cause the signal to jump up and down. In fact, Pluto might be rising higher in the sky or setting lower in the sky. So these things may not be flat. You may be overall, the signal may be getting brighter or dimmer. There may be all kinds of things you need to contend with. And your skill with handling that data is often what determines the level of success you have with a given experiment. So one of the learning goals of these exercises that we see coming up repeatedly is that there are decisions that astronomers need to make. And being skilled at making those decisions will help you get better results out of the data. How do you handle that data set? How do you deal with the fact that Pluto might be getting higher in the sky, lower in the sky, or the humidity in the atmosphere might be increasing, or that you've got this Poisson noise, you've got this statistical noise in your data? What do you do? How do you handle that? What graphs do you make? Do you make a graph that looks like this? What do you choose for the stretch of the axes of the graph? How do you fit those graphs with lines or with parabolas or with something else, second order polynomials, exponential functions? You have all kinds of choices to make. How you set up the experiment to take the data in the first place is a choice and that you made. And it's the astronomers making decisions constantly, and those decisions are feeding in to the quality of the data that feeds into the quality of the models that come out the other side. In this case, the model that comes out the other side is the sizes of these two objects that we're looking at, the diameters of two stars in a binary system, or the diameters of Pluto and Charon. So in any event, there's a lot of stuff going on here, and astronomers need to make those kinds of decisions in order to do this. And so we're really practicing this a little bit. What you'll find is the signal's going to jump around. And so our recommendation, you're the astronomer, you make the decision how you want to process the data. My recommendation, fit a flat line here, fit a sloped line there, fit a flat line at the bottom, fit a sloped line, fit a line right there, and calculate the times of those contact points. And do this work. Work right through that, finding out these diameters. That's what we've asked you to do. When you fit a line, if you're doing this by hand on graph paper with a pencil or pen, you want to fit a line. You see the data that looks like this. You want to have the amount of scatter above and below be about the same number of points below, about the same number of points above, or the average scatter of the points above. Even if there's a few more on one side or the other, the average scatter above and below, the total scatter above and below is about the same. And then figure out where those lines cross. If you're doing this on the computer, and I always recommend it if you can, go ahead and do that, and have your program fit a line for you. Then you have a formula for this line, you have a formula for this line. The formula is going to be signal. It's of this form signal, or delta magnitude as we give it to you in this exercise, is equal to this is time down here, this is signal up here, y equals mx plus b, but x is time, so it's going to be slope times time plus intercept. That's your general formula for the line. If you have a formula for this line and you have a formula for this line, you can set those two signals equal to each other. That's that point where those two signals are equal to each other, and you can solve for the time where those two things are equal to each other. And that's going to give you the time of first contact, time of second contact, time of third contact, time of fourth contact. Again, you can do this by hand. You can do this on the computer, whatever works for the situation you have right there. But if you have a formula, if your computer's telling you this is the formula for this line and this is the formula for this line, set the two signal values equal, because that's where the two cross. That's the signal value where they're equal. And then calculate the times and do your calculations. That's T1, T2 minus T1 is what that actually is right there. That time right there is T2 minus T1. And that time right there is T2 minus T4. T4 minus T2. Time keeps slipping into the future, not into the past. Keeps slipping into the future. So T4 minus T2 right there, and you have the other two cases where you can do that as well. So this is all great. This is the kind of thing you want to do You want to go out and measure those contact points and figure out the time between T2 minus T1, T4 minus T2, or T3 minus T1, or T4 minus T3. And that's going to give you these diameters of these objects. And so you're doing great work here. You're doing work that absolutely, it's work that I do with my students with the eclipsing binary stars that we have in the data set for the research that we've been doing for 2 decades here now. We have half a dozen eclipsing binaries in our field of view, and we do this exact kind of work. One of the things we're doing is we're looking for eccentricity of the orbit. We wouldn't expect there to be eccentricity of the orbits of these things, but measuring the times between eclipses, you can do that. Go ahead and look for the later exercise. I should stand here. I should realize what that later exercise is. I'm going to guess that later exercise is 23. That has the eclipsing binary data from one of those eclipsing binaries in our research data set that you can play with. And so you can see, you can do that kind of work there in that exercise. So one of the things, we have one eclipsing binary system in our field of view that looks just like this, flat outside of eclipse, nice linear drop into eclipse, flat along the bottom, nice linear rise out and flat. It looks just like the light curve that you're drawing here. And so I want you to see a couple of different situations, a couple of different geometries that came up. We drew this where we had a larger object and a smaller object. It's possible that you have 2 objects of the same size. If you have 2 objects of the same size, then as soon as they get into full eclipse, they're going to start out of eclipse again. And your light curve's actually going to look like this. And if those 2 objects are of equal brightness, in our case, that would mean equal albedo, so they're reflecting light equally. In an eclipsing binary case, it means the 2 stars of the same temperature. If they had equal brightness, then that value right here is going to be exactly 1/2 of the value up here, you see, because half the light's gone in that case. So that's a special case where you have 2 stars of equal size and equal temperature, where you get this sort of fang shape, and the bottom of the fang is 1/2 the brightness at the top. Now, if they're not the same temperature or the same brightness, if Pluto and Charon were exactly the same size, you would get this shape of light curve. And if one of them had a higher albedo than the other, then sometimes when the brighter one was blocked, this would be less than half. And when the fainter one was blocked, the one with the lower albedo was blocked, this would be greater than half up here. And you would see that bounce back and forth. It would be a way you could measure the albedos of these objects. Now, what's much more common is we get partially eclipsing systems. So you could have 2 objects that aren't the same size or are the same size, either way, but you have an object like this and an object like this that from our point of view, it just barely nips across and you just get a little bit of the light blocked, in which case you're also going to get a sort of fang shape like this. But in that case, it's just a very small amount, no matter which object's being blocked. It's just a very small amount of the light, a small fraction of the light that's gone away. This is often, in the case of the data that we take, that value could be anything, but in the case of the data that we take, that's often 90% of the full value. You see 10% or 5% of the light go away, or a few percent, as you have this small little bit of eclipse going on. Back to this, where you have a smaller object passing in front of a larger object. This is now, you go back 30 years. I'm trying to get my timing right here. For when we're shooting this, you go back 30 years, we just started to discover planets around other stars. And we started to do that by Doppler shift. That to me was an amazing thing, because the speeds of the wobbles of the stars was so small. It was like a person running sometimes, or walking, is how small that was. So you're seeing very small Doppler shifts of these things. But nowadays, we actually use occultation methods to see light curve dimmings. That's the light curve that you're making, brightness versus time, signal versus time. And to see light curves dimming, and this is exactly this. If this is a little tiny planet relative to a big star, it's blocking a little bit of the light as it moves across there, and you're going to see a light curve that looks like this. And often in that case, that drop right there is much less than 1% of the total light. But if you got really good photometry, you can measure that. And so this is an occultation method for detecting exoplanets nowadays. So this is a really important technique. Is what I've tried. There's a lot of different variations of this technique. There's a lot of different geometries. There's a lot of different situations where we apply this, and we apply this all over the place. So it's a great technique to practice and a great technique to learn, and you'll learn something about Pluto, Charon at the same time. So that's our introduction. That's what I've got for you here today. This is, again, exercise 18 in Astronomers as Observers and Experimenters from Kendall Hunt. I hope you have fun with this exercise. I know I have fun with this exercise. I have fun thinking about it all the time. Good luck, everybody. Let me know if you have any questions.